All right, hello everyone. We're going to look at another example of a Turing machine. And yeah, this one you can see is a lot more complicated than the last example. It has a lot more state transitions, and it also has some new states. So in addition to going left and to going right along the ticker tape at the bottom, it also has some other states that say yes, accept, or like return true, or no, reject, return false. So the yes and the no states are the new additions. They're going to stop the machine. The last one that we saw was sort of an infinite machine. It just kept on running and running and running. This one will actually report true or false in the end. So it's actually deciding something rather than just counting up. Okay, so what is it deciding? Take a look at the memory here, and you can see it's filled with A's and B's in addition to all of these blank spaces to the left and then to the right. We usually imagine that a Turing tape is or a Turing machine has an infinite tape. So to the left and to the right, it just extends on forever. Okay, but what we really have to focus on is just in the middle here, the A's and the B's. So what this Turing machine is designed to do is to count the number of A's and count the number of B's and decide whether there are an equal number or not. If there are the same number of A's as there are B's, then it will end on this state, and it will return yes. Otherwise, it will say no, and it will return false. Okay, so we can just take a look and count, and we can see that yes, there are 3 A's and 3 B's, so this Turing machine should end up here. Let's just watch it do that. So it's going to follow a lot of state transitions really quickly, and along the bottom you can see it's crossing out things. It's placing an X over some of them, and it arrived at Y for yes. Okay, so what was it doing? Let me back up here. Well, just like if you were going to solve the problem on your own, and maybe it were like a much longer string of A's and B's, what you might do is you might cross off an A for every B that you saw. So you cross them off in pairs. That's what this is basically doing. It's just crossing off an A and crossing off a B together. Okay, so that one ended up at yes because there were an equal number of A's and B's. Let me just show you another example really quick. I can change the memory, and yeah, let's look at this example instead. Here there are 2 B's and 3 A's, so you can see it ought to end up here at N. It will still cross off everything, but it will end up in the no state in the end. Let's see that happen. Okay, so it's crossing off A's and B's, and then it crossed off an A, but it couldn't also cross off a B, so it arrived at N. Okay, let's go back to that first one, and then go a little bit more slowly through it and see how it works. Okay, so the initial state says to go left. Now this means left along the tape. It doesn't mean go left along the graph here. That's kind of irrelevant. It says go left along the memory tape. So it'll go to this memory address -1, and if it can, it will follow a state transition. Okay, so let's try to anticipate what it's going to do. If it sees a pound sign, it will replace it with a pound sign and then arrive at this next state in which it immediately goes to the right. Okay, let's play that forward. It went to the left first, and then it follows that state transition, and then it goes to the right. Okay, so you might think, well, what did that just do? It basically just took us back to the beginning again. This little part of it was just meant to bring us to the very beginning of the word. So that now that we're sure that we are at the beginning of the word, we can proceed from here. And now you can see we have many more options. What can we do if we see an A or a blank or a B? We could follow these different paths. Now we happen to see an A right now, so we're going to cross it off, basically replace it with an X, and then continue to go to the right. So let's follow that. Okay, now we're at this state, so we're paused here. What's going to happen next? We see a B, and this state transition allows us to follow this arrow. If we see a B, we can replace it with an X, and then we're going to go to the left immediately. Okay, and now we're here again, back to where we started. So here, we don't have any state transitions for X, notice. We only have a state transition for pound sign. So what is it going to do? If it can't do anything, it's just going to go back to itself. It's going to go to the left one more time. So let's watch it do that. Okay, it went to the left, and it would keep doing that, but it has now a new path available to it. It can follow this state transition from pound sign, replace it with pound sign, and then go right. Okay, let's follow this one. And here you can see there are no state transitions if we read an X. We only have options if we see an A, a blank, or a B. So what is it going to do? It's just going to keep going to the right. It'll keep going to the right until it sees a B, an A, or a blank. So let's watch it do that. It goes to the right, sees an X, so it still has to go to the right. Okay, now we're kind of free here. Now we see a B, and we can follow this arrow out of it. It'll see a B, it'll replace it with an X, and then go to the right again. Okay, and that's the way this works basically. We just looped through something where we've seen it cross off A's and B's, and it's then going to yeah, go to the end of the word, look for A's. So I'm just kind of stepping through it now to finish it off. And it's checking for, now if it only has X's, it's going to keep going to the right, it hit a blank, and now it ends up in the yes state, or the accept state. Okay, yeah, it's very time-consuming and tedious to follow these, but it's something that computers are perfectly happy to do, right? For humans, it's a very tedious task to follow along all of these transitions and to keep track of all of these like very minute details. But computers, of course, can be very happy just following these little sets of instructions. Okay, so what we've seen is a more complicated example of a Turing machine that follows a set of instructions, and this is one that a DFA could not have done. Okay, that's all for this little video. I'll see you in the next example.